So now that we've seen a little bit about how related rates work on a graph, I do want to look at some algebraic examples. And sort of what this means is, if we have a function, or if we have a relation, can we figure out what the rate of change of x is and what the rate of change of y is? Can we find out what the relationship is between those rates and use those to find how the function is changing and moving over time? And the really, really key thing to remember on all of these problems is that this is all about how the function is changing over time. Even if the problem doesn't have time built into it, we can think about how this function is growing and changing as it moves along. So the first example I want to look at is this one. Right? Given that your relation or your function is y equals x squared, find dy dt. In other words, find the rate of change of y. Find how quickly y is changing when x equals 3 if dx dt, if the rate of change of x with respect to time is 2. So if x is going up by 2 at this place, how is y changing? So the big hint for you here, like if you're sort of looking for how to get through these problems, when you see a problem ask for dy dt, like this right here screams, hey, I want the derivative with respect to t. So if you want the derivative with respect to t, I need to take the derivative of this with respect to t. Now, you remember when we learned about the chain rule, when we learned about, about implicit differentiation, if we take the derivative of something that is not the independent variable t, I need to have dy dt or dx dt. Right? So when I take this derivative right here, this derivative is going to be dy dt, because that is the derivative of y with respect to t. Dy dt is... Now, what's the derivative of x squared? Well, it's not t squared, but it's x squared. We know how to do that. This would be bring down the 2, leave the x inside, but because that x was not t, I need to multiply by dx dt. This is just like when we were finding dy dx in implicit differentiation. The difference here is it's not dy dx that I'm looking for, it's dy dt. So, one more time, anything that's not a t, we will need to do the chain rule and effectively multiply by dy dt or dx dt or whatever variable we're working with. And at this point, this should be an easy problem to solve because we just have to evaluate. It turns out that dy dt will be 2 times x, which is 3, times dx dt, which is 2. So now my dy dt is 12. And we could look at this second example as well. This derivative setup is what's going to apply to the next problem as well, so we can just sort of bring that down. This time they want me to find dx dt. It's fine, I'll just evaluate using the other tools. Dy dt we're told is 4, so 4 equals 2 times negative 1 times dx dt. Well, that's what I want to solve for. So if I just divide both sides by negative 2, these will divide out on this side. I'll end up finding out that dx dt is negative 2. So we found that in this case, dy dt was 12, and in this case, dx dt was negative 2. When possible, I would like us to think about these things graphically. So I'm going to pause the video for a second here, and I'm going to bring up a picture of this function so we can talk about it a little bit more. So I'll start on that right now. Alright, so let's see if we can make sense of these rates. Right? In the first problem, we were told when x equals 3, so I'm, over here at x equals 3. When x equals 3, so we're looking at sort of this point on the function, 3, 9. At that point, if dx dt equals 2, in other words, if x sort of starts increasing by 2, how much should we expect y to change by? Well, the slope is pretty steep here. This function is going up quickly, right? If x were to go up by 2, y is going to have to respond by increasing quite a bit to make up for that. And we can see that here. X is only going up by about 2, y is about to go up by like 12. Now that doesn't mean that if I actually go to the right by 2, it will be up 12. It just gives us a sense for how fast y is changing compared to how fast x is changing. Let's look at the second one. In this one, we're told when we're looking at x equals negative 1. So here's x equals negative 1. We're looking at, sort of this value here. We're told if dy dt is 4, if y goes up, by about 4, and we can even sort of count that out. If it goes up by about 4, how much, so it goes up by 4, how much does x have to change by? Well, you'll notice x has to become more negative. It's moving to the left, and it has to move to the left less than y does. In fact, in this one you can even see it more clearly. This distance here looks like it's about 4. This distance here looks like it's about half of what that distance was. This really makes sense. At this point on the graph, this point right here, there is very much a sense that if y goes up by 4, the amount that x would have to change by is about 2. That's why these problems are called related rates. There's a relationship between the rates of change of these variables. So here's an example for you to try on your own. Pause the video and give it a shot. So hopefully you recognize that this is going to take the product rule. If you didn't, pause the video and try it again. So to do this one, first we take the derivative of x. Remember, we're doing the derivative of x with respect to t. So this will be dx dt, and then we leave the y, the second part alone, so y squared, plus, this time we'll leave the x alone, and we take the derivative of y squared. That'll be 2y, but because that y isn't a t, we multiply by dy dt. And this is equal to the derivative of 8, which is 0. At this point, I just need to solve for dx dt, so I will leave dx dt here, and I can evaluate using all of the other values of the variables I was given. They told me y is 1, we were told x was 8, times 2 times 1 times dy dt, which was negative 1. So if I go through and solve here, I can end up with dx dt, let's see here, plus, I guess it's not plus, I suppose this will actually be minus 16 equals 0. So that's actually pretty straightforward. dx dt, it appears in this case, is positive 16. So that covers these sort of conceptual examples. In the next video I'm going to be getting into some sort of real-world examples where we can see how this actually impacts shapes and things that we can see and work with. So I'll see you there.